Hello everyone, I am Mrs. D. Shanti Chellaya, working as Assistant Professor in ECE department. I am going to take DC characteristics in op-amps in the subject linear integrated circuits. I will discuss the DC characteristics of the op-amp. It describes the performance with constant or low frequency input signals. These static parameters often represent imperfections in practical op-amps that cause the actual output to deviate from the ideal characteristics. Ideal characteristics are input impedance is 0, input impedance is very high, output impedance is 0, and the bias currents are 0. So these deviations will arise to DC characteristics under steady state condition. It is important for precision and low frequency application. The various DC characteristics are input bias current, input offset current, input offset voltage, and temperature drift. The next characteristic of importance is input bias current. It is defined as the average of input bias currents flowing into the inverting and non-inverting terminal. IB plus is the input bias current flowing into non-inverting terminal, and IB minus is the input bias current flowing into the inverting terminal. It is ideally zero for FET op-amp. It is typically in nanoampere range for BJT op-amp, and it is picoampere range for FET op-amp. IB is equal to IB plus plus P minus divided by 2. The next parameter is input offset current. The input offset current is defined as the algebraic difference between the two input bias currents IB plus and IB minus. The mismatches in the input stage cause these currents to be slightly different, leading to additional input errors. IOS is equal to 0 if IB minus and IB2 are equal, but due to practical difficulties, IB1 and IB2 are not equal, leading to some offset current. Smaller IOS improves the DC accuracy. Input offset voltage, which is designated as VIOS. It is a small differential DC voltage required to make the output zero. It is ideally zero, but practically we have few microvolts to millivolts. While ideally zero, practical values range from microvolts to few millivolts due to internal transistor mismatch. The internet is used to design the internal diagram of op-amp. For example, mu A 741. As in the diagram, a small amount of voltage is given at the non-inverting terminal to make the output voltage 0 for 0 input voltage in case of voltage follower. The small amount of voltage is known as the input offset voltage. The next parameter is the total output offset voltage. It is the DC voltage present at the output when input is 0. This total output offset voltage is due to input offset voltage which is given at the input terminal and due to presence of bias current which is flowing into the input terminal. It causes output drift in precision circuit where the circuit is used to measure a few lower voltages in the order of millivolts or microvolts. Hence, a compensation technique is followed to make the output offset zero when zero input voltage is given. So, null pins are available in the MUA 741. Along the null pins, you can connect a potentiometer and you can adjust the potentiometer to make the output voltage zero for a zero input voltage. bias current change with the temperature. It is typically expressed in units like microvolt per degree centigrade and nanoamperes per degree centigrade. It is measured in that range, and low drift op-amps are used in high precision application. Since it is the value of the current or offset is changed with temperature, it is called as temperature or thermal drift. CMR, otherwise called as common mode rejection ratio. It is defined as the measure of the op-amp ability to reject the common signals to both the input. High CMRR ensures that common mode noise does not appear at the output. CMRR is defined as ratio between AD and AC. AD is the differential mode gain, AC is the common mode gain. Higher CMRR indicates better DC performance, that is, ideally it should be infinity, practically it is very high. So to maintain high CMRR, AD should be high and AC should be low, or it should be, ideally it should be 0. So it should amplify the differential mode and it should reject the common signal. The differential mode voltage is not same in all ranges of voltages. Hence, compensation technique should be followed to maintain higher CMR, and is expressed in the order of dB. To conclude about the DC characteristic, it affects the accuracy and stability of op-amp circuits. The offset voltage and currents are the critical parameters which should be compensated, and it is important for instrumentation and low frequency design as in the part of application.